I want to do one more example that occurs a few pages further on in the worksheet book. And here, notice it's asking for the derivative of inverse functions, and I've just given you the answer we derived previously. But now we can check ourselves in a different way, namely just being given some information about two functions, f and g, that we are told are inverse functions of each other. Can we use our new rule to determine what the derivative of g is at -2? F and g are inverse functions. Okay. So from above, we know g prime at -2 has to be 1 over f prime evaluated at g of -2. Now we have to use our knowledge of inverse functions to figure out what g of -2 is. So digging back into our memories, what do we remember about inverse functions? If f and g are inverse functions, what that means is f of x equals y implies that g of y equals x, and I should say vice versa. So we should put that in there. Okay? For our example, we need to know g of -2. It's not given to us in the data anywhere, but g is the inverse function of f. So whatever g of -2 is, using that as an input to f, better give us an output of -2. So looking at the data you have here, we see that f of 7 equals -2. That tells us that g of -2 better be 7. We can now come back to our original problem. We know what g of -2 is. It's 7, so we'll substitute that. We'll have to find f prime of 7. Here are the derivatives on this side. We're given the derivative at 7 is -2. So our answer is 1 over -2, or if you prefer, -1/2. What I'd like you to do now is practice some chain rules on your own. If you go to page 27 of the entire class printout, you will see these 5 problems. Please find the derivative for each of the functions, and I guarantee they will use one or more chain rule applications. I'm going to stop the video here, and if you go to the second video, there will be a moment where it tells you what the inside and the outside function is for each piece if you want a hint, and then there will be another one which tells you what the answer is. If you can't get from the hint to the answer, please ask questions about it in class. I recommend that you pause the recording now so that you can try these problems on your own first. If you get frustrated, hints will follow. Please don't watch these hints unless you've tried them first on your own. If you have tried them on your own, what follows is a quick delineation of what the inside and what the outside function is for each one of the problems. For our first problem, h of r equals the sine of 10r plus 3. The inside function is the argument of the sine. The outside function is the sine itself. So let us call the inside function equal to u is going to be 10r plus 3, and the outside function h is going to be the sine of u. For the second function, we're looking at the natural log of t squared plus 2t plus 1. Often parentheses give us a hint as to what the inside function is. So in this case, the inside function is going to be t squared plus 2t plus 1, and the outside function is going to be natural log of u. For the third function, this one, notice what's going on here. There is a product happening between sine of 5 theta and cosine squared of theta. So to take this derivative, you are going to have to take a product rule. And within those product rules, you will do two chain rules. One chain rule when you find the derivative of the sine of 5 theta, and one chain rule when you define the derivative of the cosine squared of theta. Let's get those chain rules set up for you. For the sine of 5 theta, the inside function is 5 theta. So if u equals 5 theta, then the outside function is sine of u. For the cosine squared of theta, remember this is the same thing as the cosine of theta all squared. The inside function is going to be cosine, so let u equal cosine theta, and the outside function is going to be u squared. For our fourth problem, g of s equals the natural log of the secant of s. Secant of s is the function which is input into the natural log as the new argument. So we will have the inside function we will set equal to u as the secant of s, and the outside function becomes g equals the natural log of u. For our fifth and final function, y equals the natural log of a product, t times t plus 1 times t plus 2 times t plus 3. We could set it up the way we did previously here in 4, where the inside function is the argument of the natural log, but then there is 4 factors, and that's going to be a lot of product rules to take the derivative of the inside function. You might want to simplify your life first by using properties of logs. Please know, or please remember, that the natural log of the product is the sum of the natural logs. So the natural log of the product, t times t plus 1 times t plus 2 times t plus 3, becomes the natural log of t plus the natural log of t plus 1 plus the natural log of t plus 2 plus the natural log of t plus 3. Now each one of these terms is going to be a chain rule. The inside function for the chain rule will be the argument of the natural log. The outside function will be natural log of u. I hope that helps you go back to work on the problems that you didn't get started on before. I hope you will again pause this recording and go back to work on those problems. When you are ready to check your answers, start this up one last time. All right, here we go. The derivative of sine of 10r plus 3 is 10 times the cosine of 10r plus 3. The derivative of the natural log of t squared plus 2t plus 1. After you put things in lowest terms, you will end up with 2 divided by t plus 1. Perhaps the most challenging one here was the derivative of L of theta equal to sine of 5 theta times the cosine squared of theta. This ends up being 5 cosine 5 theta times cosine squared theta minus 2 sine 5 theta sine theta cosine theta. You might ask, what kind of simplifications can you do here? But you could factor out some common factors like a cosine theta. But aside from that, I think it's good just to leave it in this form. The derivative of the natural log of secant of s is surprisingly beautiful. It ends up being tangent of s. And finally, the derivative of the natural log of the product t times t plus 1 times t plus 2 times t plus 3 equals 1 over t plus 1 over t plus 1 plus 1 over t plus 2 plus 1 over t plus 3. There'll be one more part to this video, which will look at implicit differentiation as the final application of the chain rule.